Syzygy episode 54, Black Hole Redemption. And welcome back for another edition of the Syzygy podcast. My name's Chris Stewart, sitting opposite me at the table here in her office, as ever, Dr Emily Brunsden. Hi, Emily.
Hello, hello.
So today we're talking about something a bit curious. We've talked on this show before about supermassive black holes at the centre of galaxies, right?
Yes.
Big swirly galaxy thing and big monster black hole thing in the middle. And that's very cool. But recently there's been some research that's kind of shown that these supermassive black holes have influence on making stars, but not just in their own neighbourhood, very, very far away. These are supermassive black holes in the centre of galaxies which are making stars in completely other galaxies, which sounds ridiculous, Emily. That doesn't sound right.
Amazing. It's so exciting.
Okay, so we're going to be pulling that one apart today. But before we do, a little bit of follow-up on some stuff we've talked about before. We've talked about Hayabusa.
Hayabusa 2.
Hayabusa 2, which was a spacecraft, Japanese spacecraft, which went to say g'day to an asteroid.
Yes, a near-Earth asteroid.
Yeah, and apparently it's coming back.
Yeah, so one of the primary mission goals of the Hayabusa 2 mission was to collect samples from this asteroid.
That's right, because it sent a little thing down, didn't it, onto the surface.
We talked about these little things that were going to kind of explode onto the surface.
Oh, and then, they were going to shoot the surface, weren't they? And knock some stuff off and then hoover it up or something?
Yep.
Yeah.
So it's done all that,
collected
some samples, and it's on its way home.
It's coming home. So we not quite sure when it's coming back, but it will be back soon, and that will be bits of near-Earth asteroid coming back down to Earth so we can study them and learn what? What are we going to find out?
So we want to know things about the early solar system, because these are some of the earliest objects that we have. They're kind of things that never made it into a planet, so never got changed by planetary geological processes. So we can trace basically what the solar system was like in its very, very early days.
Very cool. I can't remember. Is this the first time we've done this?
It's the first time we're going to have really good samples. I think the first time we tried, the lander didn't quite make it onto the ground. So
that's the hard part.
Well, it made it to the ground, but maybe not in as many pieces as you would hope it was.
Yeah, the hard part is sticking the landing. Getting to the ground is not so hard, but actually, making it in one piece. So good luck, Hayabusa 2, and looking forward to following that one up when we actually have some data to look at. That'll be very cool. But listen, on with the topic du jour, which is bloody huge black holes doing things in other galaxies. What is going on here, Emily?
It's amazing. Yeah. So what I'm going to do is I'm going to walk you through kind of the process, and then we're going to roll this all the way back and think about the geometry of what's going on, and then we'll look at each of the kind of processes a bit different.
Sounds good.
On their own, because it's kind of this happens and this happens, it triggers this, it does this, it does this, it does this. It tells a really nice story.
All right. We've got a story, we've got a narrative. Let's do it. Where do we start?
Okay. So we start with the supermassive black hole. Okay, this particular supermassive black hole has a jet, right? That jet is creating shocks in the intergalactic medium, so the space between galaxies. This is heating an enormous bubble of gas, which produces X-rays, and it's these that go into the other galaxies and compress the interstellar medium in other galaxies. So the space between stars, all this gas and dust, which triggers stars to be born.
Wow. Okay, there's a few steps there, and if I've followed that at all, okay, really active supermassive black hole, big amount of energy going out, basically creating a kind of bubble shockwave sort of thing, which is then through various steps that you outlined, making stars in another galaxy. Who's found this? Do we have a
so this is a paper by Gulli et al. Who published this in ANA in September. So this is really exciting new stuff.
And hot off the presses.
Yeah, and they've used a whole lot of different telescopes. So we'll talk about all the different interesting telescopes they've been using along the way to kind of trace this story of the supermassive black hole and the new stars.
Excellent. All right, so let's start pulling this one apart. We've got a lot of steps to go through here. So, Emily, where do we start?
Okay, so first thing to talk about would be kind of to give you an impression in your mind about what the geometry of this situation is.
Okay.
So the thing to remember is that we're always told that space is huge.
Yeah, space is big.
Yeah, there's a lot of space in space, it turns out. But
hence the name. Yeah.
Some space is bigger than others. If that
that does make sense. Well, no, it does. But let's see if we can get a bit of a grip on that. So help us out here.
Okay, so one example would be if you took the sun and you shrunk it down to the size of an orange.
Okay, we're going to do this, aren't we?
Yep.
Okay,
I
so
love
the sun
the
is an
oranges.
orange.
Sun is an orange. Then the next star that's closest to us, Proxima Centauri, is something like 2,000 kilometers away.
That's a lot of space between stars.
Yes.
So we've got an orange and 2,000 kilometers away. So, like, what's that? Over somewhere towards Russia.
It's halfway to the North Pole.
Halfway to the North Pole from us here in York.
Yep.
So quite a long way. Let's say Norway, right? We're up in Norway, and that's the next orange.
Yep.
Another orange in Norway. Great. Okay, so that's the space between stars, but that's just to the nearest star.
Yep.
There's a lot of stars in our galaxy. So,
and there is a lot of space, basically.
Yeah. Okay. So that gives us an image of space between stars. Next step.
Okay, space between galaxies.
Okay.
Okay, so we are the big Milky Way galaxy, this grand spiral. If we shrunk that down to the size of an orange.
Okay, so now the orange is not a star, it's a galaxy. It's our galaxy, yes.
Then the Andromeda Galaxy, our nearest big neighbor, how far away?
Well, I think we've done this before, and I was completely I was out by an order of magnitude, but I seem to remember it was the other side of your office, wasn't it?
It's 2 meters.
2 meters away.
Yeah.
So not even. It's over by
halfway.
over by your desk over there. So 2 meters away, and 2 oranges 2 meters apart.
Yeah.
And that's the space between galaxies.
Yep.
So huge amounts of space between individual stars, but then you take the next big leap out and you're looking at the next building block, which is galaxies, and you've got that seems comparatively close.
Exactly, yeah. So the space...
If you measure that in actual kilometers, it's a huge amount of space, but sure.
So the space between galaxies can be relatively small compared to space being big, which it is as well. Yes.
Yeah.
So this is one of these systems. So we're in a group of galaxies called the local group.
Mm-hmm. Imaginatively named.
Yep. But this is another kind of structure of galaxies called a cluster. Mm-hmm. And it's got this galaxy in the center of it, well, towards the center, which is called, would you like to know?
Yes, please.
SDSS J1030 plus 0524.
Very nice.
Yeah.
Very nice. Just rolls off the tongue. It's poetry.
Which is actually, it does kind of make sense because the SDSS stands for the Sloan Digital Sky Survey.
Right.
So that's the way that they kind of catalogued it. And then the rest is based on its coordinates. So this is...
Okay, so it's meaningful to someone, just not the rest of us.
Yeah.
Yeah, sure.
I mean, we can call it Bob if you like.
Sure. Okay. Or, whatever. Anyway, cluster of galaxies.
Yeah. And
we're imagining distance between them as oranges separated by 2 meters. Fine.
So this whole cluster of galaxies, I'm going to use the scale of light years. And I'm actually going to use millions of light years and drop the millions because it kind of helps to get the scale in your mind. Right. Okay. So if I'm going to say 1, what I really mean is 1,000,000 light years. Okay.
So everyone just recalibrate in your heads. 1 million light years. We're just going to be talking in units of that from now on.
Yeah.
Okay.
So this is kind of a disc-ish shaped galaxy. It's about 0.1 across, right? And it's got a jet poking out from the center, which is perpendicular to the disk structure. And that jet is 1 long.
Okay, so it's 0.1 across, and the jet is 1. It's a really big jet.
So the jet's 10 times bigger than the diameter of the galaxy.
Wow. So when they call these things active galactic nuclei, they're not kidding around.
No.
That's some serious activity going on there.
Exactly, yeah. And we'll come back to what's going on to cause that.
Yep.
Now, the jet's 1 long, and there are somewhere around 4 to 6 other galaxies that are kind of, to us they look like they're in an arc shape, but there could be some 3-dimensional element to that. But they're all about 1.3 away. Okay,
so the jet itself is 1 in these units, and the other galaxies are in the order of that or a little bit more away.
Yep.
So that jet is totally big enough to start mucking around with other galaxies.
Exactly.
Is the point.
Yeah.
Okay.
And then the whole system's about 10 away from us.
Away from us.
Yeah.
Okay.
Hang on. No, I've missed off some zeros there.
Oh no.
It's 10,000. Sorry.
Yeah, that makes a big difference.
Yeah. 10 wouldn't be far enough away.
No.
Yeah. So the Andromeda is 2.5 away from us. These galaxies are 10,000 away from us.
Right. Okay. So that's the distance scale between clusters of galaxies. So within our cluster, we're sort of oranges separated by 2 meters. And then clusters are a much greater jump again to the next cluster out. Okay.
Yeah.
All right.
So there's probably something like 8 galaxies in this cluster in total, or at least 8 that we've seen. There's actually probably a whole lot more than that we can't see because this is actually incredibly far away and not something you can just sort of roll your hobby telescope around and have a peek at.
Yeah. I mean, you can see in the night sky with a reasonable telescope, or maybe even, I don't know, can you see Andromeda with binoculars? You
can see it with the naked eye if it's
on
dark
a really
enough.
dark, clear night. Yeah.
It's actually really huge across the sky.
Yeah, I mean, it is. It's much bigger than the moon. Staggeringly, it's just really quite dim. But getting out to the next cluster of galaxies, you couldn't see that with the naked eye. You couldn't see that with a hobby
Andromeda is the
telescope.
farthest thing we can see with the naked eye.
Right. Okay.
Yeah.
Okay, so this is with some serious telescopage.
Indeed, yeah. So and just to see these kind of structures, then there's 2 big telescopes that we used. So, and I mean, this is going to sound like it's not a lot, but they use 6 hours of VLT, the Very Large Telescope in South America. 6 hours of observing time is not insignificant on these big instruments.
Yeah, I mean, that sounds like a lot to me.
That's a lot, yeah.
So that's looking at a patch of sky and just saying, we're just going to lock on that and just let the light just keep coming in until we can finally properly image this thing with enough light over 6 hours.
Yeah, so it's a bit analogous to an exposure. The longer you leave it, then the more light you can get.
Yeah, that's quite a lot.
Yeah. And they also had 4 hours on the Large Binocular Telescope, which is in Arizona. So
I didn't even know that was a thing. I like it.
Yeah, it kind of looks like a giant owl.
What's the utility of binocular is it just to have 2 apertures, or is it?
They use it to do interferometry with the infrared part of the spectrum.
Okay.
So the stuff that we do very commonly with radio telescopes, we've talked about the VLA, actually the VLT, you can do some interferometry as well with the multiple dishes. You can combine the several dishes together to get a increased signal, basically.
Right. Okay. So if you've got 2 dishes, then you can do very, very clever things with the overlapping of those two images.
And really, where you win is with resolution. So you can resolve smaller details using this technique.
Very cool.
Yeah. So that's just to get the sort of optical / infrared images of these objects. And then I guess if we go back to looking at the kind of the story of what's actually happening here, we can walk through all those little bits and see what's going on now that you can picture it in your mind.
Sure. So we've got an
image.
image of what this thing is, right? Yeah. We've got a cluster quite a long way away. And now we need to dig down into, okay, so we've got this big jet coming out, which is of the order of magnitude of the distance between the galaxies. Yep. So what's it doing?
Well, okay, so if we go back to where it's even coming from, this is helpful to think about why that jet is there.
Okay.
So there's supermassive black holes and there's supermassive black holes.
super uber massive. Yeah.
Basically, some supermassive black holes are special.
Yeah.
And these are the ones that we call AGN, or active galactic nuclei. So some these supermassive black holes are actively feeding on material. Wow, that could be sort of leftover bits of stars or bits of gas and dust that's come from their interstellar medium in the galaxy. And this kind of feeding process releases huge amounts of energy. So they're kind of like normal supermassive black holes on steroids with
common
a
or
lot
garden
of energy.
variety, but with a lot of energy because they're feeding.
Yeah.
And as they sort of draw stuff down around into the black hole, a lot of energy is given off as a result.
Exactly. Yeah. Now this supermassive black hole is already a monster in terms of what we would count as supermassive black holes.
What would we consider a monster of a supermassive? I mean, supermassive is already monstrous. So this is...
We kind of need ultramassive.
This is sort of Godzilla style. What is this thing?
So the supermassive black hole at the center of our galaxy is something like 4 million times the mass of the sun.
Which is non-trivial. That's big.
30 million suns in something smaller than the solar system is a pretty... powerful black hole.
Yeah, I think that warrants the name supermassive. Good. Yeah. So this one that we're talking about?
30 million.
Hang on, what did we just say it was?
4 for us, 30 million for this other one.
That's a lot.
Yeah.
Yeah.
So it's nearly 8 times bigger.
Okay.
And it's a type of object that we call a QSO. And some of these names are kind of slightly historical. So a QSO stands for quasi-stellar object.
Okay, so it's a supermassive black hole that's an AGN that's a QSO.
Yep.
Why is it quasi-stellar?
Because when we first started spotting these things, they just looked like stars.
Oh, I see.
They kind of looked like smudgy stars.
Right.
And then once we realized that these were quasi-stellar objects, or quasars is another term you might have heard, is they realized just how distant these objects were, because they kind of looked like a star that was just a bit smudgy. But then when we measured their spectra and looked at what they were made of, they didn't have spectral lines anything like a star should have. But then we eventually figured out that they didn't have the spectral lines that stars have, because they were so redshifted that, say, the normal hydrogen lines that we'd see in the optical part of the spectrum were moved all the way into the infrared by an enormous redshift.
So a redshift, and this is like a Doppler effect, right?
Yes,
the red shifting, in the same way that, when you hear a car going past and you hear it go from high to low, the sort of style, that's an audio Doppler effect. This Doppler effect is for the wavelength, frequency, the color of the light. So what does redshift mean in this case?
So it means that the galaxies, or the quasar or QSO, is moving incredibly fast away from us.
Right. And in cosmology, that's a proxy that you can turn that around and say, if it's moving away from us very fast, then it must be a very long way away.
Yes.
Because of the expansion of the universe. The further away you are, the faster you seem to be moving away from us.
Yep.
Yeah.
So once you know that this object is really, really far away from us, you start thinking, actually, there's no way that this is a star.
This isn't a star.
We would not see a star at this distance. You'd need something to be millions of billions of times the brightness of a star to be able to see it at these distances.
Which it turns out it is, but it's not a star.
Exactly.
Okay,
exactly. So it's the center of one of these galaxies. So that's where they got the name from.
So that's historical and historical in the naming. But it does make me wonder, it was about 100-ish years ago. This is just a little tangent going on here. About 100 years ago that we even realized that there were galaxies, right? Or other galaxies. We're in one and there are others. When did we find out that there are clusters? Like, we've got our local group, and Andromeda we can see in the sky with the naked eye on a decent dark night. But how long ago was it that people went, oh my God, look, this smudgy star thing, that's actually a whole other galaxy really far away? When did that happen?
That's a good question. I don't know exact dates, but I don't think it took very long, because we had really good ways of measuring distances to these objects with Cepheids to begin with. And then once we started measuring redshifts, so these... when we had the understanding that the universe was expanding. I mean, this is before we knew that expansion was accelerating.
Yeah.
But I think we were getting good values for the Hubble constant by the 1960s. So
right. Okay.
It must have been somewhere in the intervening period between the 20s and the 60s that all this got really well developed.
Right. So it's still a while ago. It really boggles my mind to think how much stretching had to go on in the minds of astronomers and cosmologists in that period of time between, okay, so it's us and a bunch of stars. No, actually, we're in a galaxy. In fact, there are other galaxies. In fact, holy cow, there's actually quite a lot of them, and some of them are really far away.
Yeah,
anyway,
really
okay.
exciting. So to go back to this quasar, we've looked at this with Chandra, which is one way you might want to look at the centers of these very active galaxies.
So sorry, what's Chandra?
So Chandra's an X-ray telescope in space, and why we want to look at it in X-rays are super energetic, but when you have these feeding black holes, they don't just have the jets, which we're going to talk about in a minute, but they also have disks of material which forms some of that inner disk is what's falling into the black hole,
right, and
creating the energy source.
So it's sort of your classic image of a black hole of something in the middle with stuff swirling around it, and it's an accretion disk. Is that what we call it?
It is, yeah.
It's a big disk of material which is swirling around this thing. Some of it falling in.
So that disk gets incredibly hot, and that's where some of the X-rays are coming from. Kind of really high energy interactions in this disk. So just by looking at the center of this object, this supermassive black hole with Chandra, then we managed to make a measurement of how bright it is. And it turns out that it's 4.5 times 10 to the 38 watts.
Anything 10 to the 38 is a hell of a lot. But let's try to put that in some kind of context, okay? a light bulb.
Yeah,
A
no,
light
that's
bulb is
probably
like a
not a
couple
good
of
thing to
watts,
try and
maybe
compare
10,
to.
or old school light bulb that's
Maybe
like
we could
60
compare
watts.
it to the entire Milky Way galaxy.
Okay, that's probably more
If
sensible.
you took all the light from the entire Milky Way galaxy,
Yep, like all the stars in our galaxy. Yeah.
that would be 1/100th of this, just from the center of this galaxy.
Good God. So this thing is 100 times brighter just by itself than our entire galaxy.
Yeah, and that's
Right.
not including the rest of the galaxy. It's not including the jet.
Wow.
Yeah, these things are powerful.
Yeah.
Powerful objects.
There's a lot going on here.
And then if we look at move on out from the QSO itself and into the jet, we've been able to image the jet with radio dishes. So radio is a useful tool to looking at really, really high energy environments, because when you get high energies, you get things like high magnetic fields,
Right.
and you get charged particles doing wonderful things in magnetic fields, which gives off a lot of radio emission.
Which is interesting, isn't it? Because, I mean, you were just saying a minute ago, you can use X-ray to look at really high energy things, because high energy things give off high energy radiation, which is X-rays, right? And so use the X-ray telescope to see that directly. But high energy things also cause other stuff to move around, big magnetic fields, other material whooshing around in the effects of these really high energy jets, which give off much lower energy, lower frequency, longer wavelength radiation, which is radio waves. So you can see it both ways, both ends of the spectrum.
Yeah, it's quite useful. And a lot of really energetic phenomena that we have in the universe, we look at both in the very high energy and also in radio as well. So these were measurements done by the VLA, so the Very Large Array in New Mexico. So this is 27, 25-meter radio dishes. So again, doing this interferometry, combining all the dishes. There's also observations on the giant meter wave radio telescope, which is similar concept, except they've got 30, 45 meter dishes.
Wow. So hang on. How many telescopes, forgetting the fact that some of these are multiple dishes, how many telescopes are we up to now? We had Chandra, we had the VLA, we had the one that you just mentioned, we got the Binocular one.
VLT.
We just, we're up to, half a dozen now?
This is serious astronomy where you've got to go out and think, what observations do I need next, and what wavelength, and with what are the best kind of telescopes that we're going to have to do this.
Or what combination of wavelengths. So we need to pull everything in.
Exactly. I think this is a great example of that. They've really tried to look across the entire spectrum.
How hard is it to coordinate that? I mean, if you're looking for time on all of these telescopes, it's hard enough to get time on one.
Yeah, it is hard.
You'd have to pull in some favours here.
Well, you've got to submit proposals, and the more data you collect, the stronger your proposals become, because you can say more interesting things about them. So you can sort of climb up the priority list by getting more and better data. But as this is going to be ongoing work, I mean, I've still got a list of telescopes at the bottom of my notes.
We're not done yet.
No, that we're going to look at. So it's really cool, though, I think, that we really are using every tool we have available to try and understand these systems.
All right, carry on. We've obviously got some stuff to get through.
Yes, okay. So this jet, this has mostly got kinetic energy being released in this jet. So the jet's shot out perpendicular from the supermassive black hole. The jet alone has got 6.3 times 10 to the 38 watts of energy.
So how many times our galaxy is that?
So that's nearly 150 times.
Just huge amounts of energy.
Crazy.
And that's coming just from the matter which is falling down into the supermassive black hole from the accretion disk.
Yes.
Ripping itself apart.
Well, you say just.
Just. I mean, it's a lot. It's
turns
big.
out atoms have got a lot of energy.
Sure. I mean, relativity and all of that. Thanks, Albert. But that's amazing.
Yeah.
It's absolutely extraordinary.
Yeah, it's a really, really exciting system. So this jet is what we see in the radio, and it's this jet that's then interacting with the intergalactic medium, which is the stuff between galaxies, to create the shockwaves.
Right. Now, this is where we should probably just pause for a second and say, just as a reminder, space isn't empty, is it?
It's definitely not
We talk
empty.
about the vacuum of space, but it's not. It's pretty dispersed, but it's by no means empty. So what's in it?
So I think the intergalactic medium is one of the most surprising things in astronomy. So instead of being kind of this very cold, almost empty region, it's actually really, really warm.
Okay. Comparatively?
Yeah, well, no, just warm. So the intergalactic medium is a really warm, very diffuse gas. Now, what you have to do is put aside, I guess, your ideas of what temperature means as a civilian on Earth.
It's warm with an asterisk. Okay.
No, it's warm physically, because the way we measure temperature is based on how fast particles are moving.
Sure. Yeah.
Now, and here, when we were talking about, it's freezing last night, that felt very, very cold. But also, we're in a very dense environment. There are a lot of atoms per square meter. So that temperature is dependent on the atoms per square meter. So when we're talking about hot in terms of the intergalactic medium, it's because it's very diffuse that it can get very, very hot.
Okay. So what you're saying is, while there aren't terribly many of them, each individual particle, atom, molecule in the intergalactic medium has quite a lot of energy.
Exactly.
There's just not many of them.
Yeah.
So it's hot, but diffuse.
Yeah. So if you stuck your finger out, it's unlikely that your finger would interact with one of those particles, so it would feel incredibly cold.
Right. Okay. But actually,
the physical
even though
measurement,
you'd be yelling with pain and then dying, you could at least die safe in the knowledge that it's actually quite nice and toasty outside.
Yeah.
Right. Okay. That's nice to know.
Because there's only something like 1 atom per meter cubed in the intergalactic medium.
That's not a lot.
It's not a lot.
It's not a lot.
So you're not going to feel warm. But as we say, when we define temperature in physics, this is, it's very, very warm. So it's something like 10,000 to 100,000 Kelvin. So degrees, it's kind of the same at this point, right?
That is really quite warm.
Yeah.
That's not warm. That's actually really, really hot. But
Yeah.
only one of those per cubic meter. So it's not a lot.
So this is probably towards the upper end of that. So we're
Right.
looking at, 100,000 degrees.
Okay.
That's the intergalactic
Now,
medium.
one atom molecule, one thing per cubic meter sounds like not terribly much at all. But I guess in the huge amount of space in between galaxies, that actually adds up to enough that you could actually put a shockwave through it, turns out.
Well, amazingly, and this is my fun fact for this episode.
Okay, go for it.
About half of the atomic matter in the universe is contained in the intergalactic medium.
What? Half?
It's
That's
amazing.
No.
It's amazing.
Space is big, right?
Yeah.
So even with almost, to within a small correction, nothing in it, that huge amount of space actually has half of all the stuff.
Yeah.
That's extraordinary.
It's amazing, isn't it?
So if you put it that way, sure, okay, there's enough out there to put a shockwave through, okay?
Yeah. And there is, to be fair, there is a region of the universe where there is less than this, and avoids which we talk about when we talk about large scale structure. So
I think we need to do a
gaps.
whole other episode on that, because that's like, you want to talk about stuff that blows your mind. It's the large scale stuff that I just think, hang on, what?
So when we talk
let's
about
come back
cosmic
to that.
voids, they're not this
Yeah.
intergalactic medium. That's really void.
All right. Could we write that on the board? Can we
Yep.
do large scale structure? Thank you. Good.
Very good.
Save that for next time.
So yeah, so there is stuff in this intergalactic medium, which is what the jet is interacting with, and it's shock waves created by this jet as it sort of plows into this intergalactic medium that cause X-rays to be emitted as well. So Chandra's been observing the jet and been observing these emission of X-rays from the shock of the jet hitting the intergalactic medium. But the shock doesn't just stop. And the X-rays just don't stop.
Yeah.
They keep going and they travel into these galaxies. Now, these may well have been just ordinary galaxies minding their own business out there in space.
Trooping along, doing what galaxies do.
Yeah, and what galaxies do is they're basically star recycling factories, right?
Okay.
You have this very broad brush evolutionary process where you have gas and dust in the interstellar medium in galaxies. That collapses down, a star's formed, the star goes through its life cycle, it dies, it puts things back out into the interstellar medium.
Typically by having bloody great explosions. Yeah.
Well, some of them do.
Some of them. Yeah. Okay.
So and then the whole cycle repeats, and you just go through this kind of evolutionary process. But you can change the speed and the rate at which this process happens by sending extra energy into the system.
You can give it a kick.
Yeah.
Okay.
And if you put shockwaves through, even a physical shock will compress interstellar medium in different ways than it would have naturally just come to form together. So you trigger the collapse of new clouds, which triggers new stars to be formed.
So, you can, as you say, you can quite literally give it a kick with something like, I don't know, an enormous, super energetic jet from an uber-massive black hole in the next neighbouring galaxy, for example?
Exactly.
Right.
Yeah.
And that's what we're seeing.
Exactly. Yeah. And so these galaxies, now these galaxies are forming somewhere between 8 and 60 solar mass worth of stars every year.
Okay. Trying to get a bit of a grip on what that means. Between 8 and 60 solar masses worth of stars.
Yeah. So that could be 8 to 60 suns, or it could be, it's actually probably a lot more of the lower mass side of stars. There's probably more stars, but they're lower mass rather than lots more that are higher mass.
But something in that order.
Yeah.
In the order of sort of tens
of
maybe
stars
hundreds.
per year.
Yeah. Okay.
So in the Milky Way, we're forming basically one.
Okay. Right. Only one.
So again, this is at least an order of 10 times magnified star formation.
Because of the jet.
Yeah.
How are we seeing that?
So we see it because when you trigger new stars to be formed, they change the overall colour of a galaxy.
In what way?
So it makes it bluer.
Okay. Why is that?
Because what you're doing is you're taking out energy that's being emitted in the red from the interstellar medium, mostly the dust that's in the interstellar medium that re-radiates back the starlight into the red part of the spectrum. You're also forming a few more blue stars, and so that's also going to contribute to the bluer end. So you kind of skew the colour of the galaxy towards the blue.
So is that how the researchers are actually getting a grip on how much activity, how much star forming activity there is in this galaxy, is by looking at its color and looking at the balance of the color across different wavelengths and saying, well, the only way it could be this color is if it's forming this many stars, at this rate. And the only way that could be happening is if it's being given a good hefty kick from the big black hole next door.
And our models are pretty good for this because we understand other things that trigger star formation in galaxies, particularly interactions with other galaxies. Mm-hmm. So again, gravity can also cause kind of disruptions to the interstellar medium, which kicks off star formation.
Right. So if two galaxies sort of bash into each other, then that can cause a whole bunch of new star formation.
Yeah. And we've got tons of examples of those. So we understand that process pretty well.
Sure. Okay. But in this case, you've got a pretty good indication of, hang on, but what about this quasi-stellar object just over here, which is ridiculously energetic? Do you think that might have something to do with it? Yeah, it probably does.
Yeah. And so what I really love about this is because I think black holes in general, and maybe particularly supermassive black holes, have a really bad reputation.
They do, rather. I mean, they're always the bad guy in the black hole movies, although I guess Interstellar not so much, but yeah.
But I'm not going to name names, but one of my friends asked me just the other day, are we in danger of being sucked into a black hole anytime soon?
Not unless they do actually make one in the Large Hadron Collider, but I think we're probably okay on that front.
Yeah. I mean, but this is, and I'm not, don't want to tease anybody, but this is really the misconception that exists about black holes, that they're kind of roaming wild through the universe, these unseen scary objects that could eat us up at any time.
Yeah. Or, the supermassive one in the center of the galaxy, presumably over time is just going to eat us all.
Yeah.
That's pretty scary.
And none of those things are going to happen. But I'm surprised there's not more science fiction films about them, to be honest.
Yeah. Do you get that a lot? I'm always curious as to, different branches of science. What are the questions that you get when you go to a party and someone says, what do you do? And you say, I'm an astronomer. What do you get?
Yeah, I often get things about black holes, actually. Yeah. And because if I say pulsating stars, if they ask me what I study, then that gets confused with pulsars. And I get that because they sound similar.
Yeah.
But they're really, really not similar. Yeah. But I think most people are really receptive and really interested in what you do. But yeah, you do get unusual questions, and black holes are definitely up in the top 5 of questions that I get. Are we going to get eaten anytime soon?
Yeah, I mean they do get it. They do get a bit of a bad rap, and it's completely understandable because the way they've always been described as the monster lurking at the core of the galaxy, or this amazingly energetic thing which is gobbling up another star or something along those lines, right? And
so let's just set the record straight. There are no black holes that are going to consume the Earth. They're not roaming through the galaxy.
We're okay.
We're okay.
Plenty of other things might kill us, but not that one.
Not that one. And also the black hole, the center of our galaxy is fine. We're going around it. We're very, very far away from it, and it's not going to do anything exciting anytime soon.
Okay. Doesn't make it any less cool. It's just not deadly.
Yes, exactly.
Okay, good. So this is adding another aspect to that, which is, black holes can make new stuff.
Yeah.
You know what? They're responsible for new stars in completely different galaxies. And so how cool is that?
So, yeah.
High five supermassive black holes.
Even in astronomy, black holes have the reputation of destructors, right?
Yeah.
They destroy stars. They tear them apart. You know, the definition of what this active galactic nucleus is something that's ripping other objects apart.
Yeah. I mean, to be clear, that is awesome.
Yes.
Like, that's not a bad thing. Right? Astronomers don't sort of go, oh, I really hate it when black holes do that. I liked that star and now it's coming. No, like this is really good stuff, right? But this is different.
Yeah, it is. And also you get negative feedback, which means that black holes stymie star formation is an understood process as well.
So hang on, how does that work?
So if you've got your black hole with this enormous jet, first of all, it's going to heat up the local region around it. So the whole center of the galaxy is going to get heated up.
So we're talking within its own galaxy now.
Within its own galaxy. So you get this extra heating that goes into the center of the galaxy, and that can heat up everything so it's too hot to form new stars, right? So that's stymie star formation. It can also blow out all the kind of material that you would normally form stars out.
I guess if you're that energetic, it's like, we would form stars if you just leave us alone for a bit. But no, you've got to just be this energetic dude in the middle who's like, no, get away, boom.
Yeah, so it's pushing all the gas and so on away, which rarefies
Trying
it.
to form a star.
It then gets too cold to be actually able to form new stars. So this negative feedback means that black holes, even these supermassive black holes, do have a reputation of slowing down star formation in their host galaxies.
Yeah.
So, but there are other processes which they can trigger them. But this is the very first time we've been able to see a black hole trigger star formation in another galaxy.
Which is, okay, that's very, very cool. I mean, black holes triggering, as long as you're far enough away, so you get a bit of distance. It's like on firecracker night. Don't get too close to where the firecrackers are going. Stand back a little bit and you can see the effects properly. But if you get in too close, that's a bit dangerous. So don't go, kids. This is a public service announcement. Don't get too close to the supermassive black hole. Step back a little bit and watch it from a distance, and all's good. That's the idea.
Appreciate its beauty.
All right, so there you go. Supermassive black holes always get a bad rep, but we've just completely resurrected that. I think thumbs up to supermassive black holes. Emily, you said a little while ago that we hadn't got through the full list of telescopes. Do you want to just quickly take us through what did we miss out there?
So I really enjoyed the future work section of this paper because they're really ambitious and they're going to go and really study the system in even more different
because we
telescopes.
haven't done it enough with, half a dozen or more telescopes so far. Let's bring in all the others as well. So quickly, what have we got?
They've already got more new ALMA. So ALMA is the Atacama Large Millimeter Array. This is microwave observations. We've got the VLA again, so more radio observations. LOFAR is another radio structure in the Netherlands. So, this is going to be someone's lifetime's work,
Let's do all the telescopes and really study the hell out of this thing. I think that's cool. I really like it. Well, unfortunately, we are going to have to wrap that one up there. So let's leave the black holes to do their star formation and step back and enjoy it from a distance. Emily, if people wanted to get in touch with us on this show in order to say hi, to give a big shout out to their favourite black hole, or to ask us a question, throw us a comment, how would they do that?
Well, Syzygy Heart Twitter.
Yes.
So SYZYGY pod on Twitter. You'll find us there. But it turns out that we quite like that handle and we use it elsewhere as well.
That's right. We're on the Instagrams. You can go and find us on Facebook. And we have a website.
We do. It's a beautiful website that Chris has built.
Yes, very nice.
So if you want to see some lovely images that go along with this, for example, we're going to put up the map of showing you just exactly how the geometry of this amazing system looks. Then you can check all that out on syzygy.fm.
Yes, indeed. You can go and find all of the past episodes there as well with all of their show notes. So you can look up all of the stuff that we've been talking about for the last, 54 episodes, including this one, plus a couple of extra bonus ones thrown in there as well. Listen, if you want to help out the show, there's a bunch of different ways that you can do that. First of all, tell your friends. Tell everyone. We want as many people to share in the joy of the universe that we want to bring through this show. So go and tell people. Give us a review, a rating, a couple of stars on your podcast player of choice. Go to Apple Podcasts or Spotify or wherever you catch us and give us a review. That really does help us rise up through the noise. And the last thing is, if you would like to become a financial supporter of the show to help us do things like the Podcast Social Club Festival that we went to up in Thirsk and all sorts of other live events to help us just keep the lights on here in Syzygy Central, go to patreon.com/ patreon.com/syzygypod. And there you can see all the different options for signing up to become one of our fabulous patrons. And we would just forever love you and put you on our great wall of thanks on the website. Otherwise, we pretty much got to wrap it up there. So thanks very much, Emily. We'll catch you next time.
See you later.
Bye-bye.